Hello, everyone. Good morning from Seattle. Welcome to my talk. I'm Xiaowei. I currently lead the computing engine team at Alibaba. Before that, I worked at Facebook, Microsoft, and Stratify. Alibaba has the world's largest e-commerce platform, Taobao. Hundreds of millions of users shop on Taobao every day. Improving their experience is our top priority. In today's talk, I'm going to explain how we are doing this in our search and recommendation services. When users interact with our platform, when this happens, the hope is that we can analyze such interactions, understand our users better using machine learning techniques, so we can give our users better results in search and recommendations. All these different interactions generate a lot of events. These events eventually get collected into an event queuing system, such as a Kafka. So the first stage in doing machine learning is feature engineering. Here, we want to ingest all these events into our system as event tables. And we use Flink for doing that. In this step, Flink will clean up the data and do whatever necessary normalization needed. The events that we ingested may not contain all the information relevant for that interaction. For example, when a user clicks on a product, clicks on a page, we do not record all the information about the page and the user themselves, but we only record the product ID and the user ID information. So to figure out the detailed information about the product and about the user's profile, we will need to look it up in some entity tables, in the product table or user profile tables. These tables are usually stored in some other systems. And a typical example is a database. So the second step that we are doing is we are going to synchronize the content from a relational database into dimension tables inside our system. Again, we use Flink for such kind of synchronization. Flink can do such synchronizations at real time. Whenever there is an update in the upstream database, Flink will immediately update the corresponding records in our dimension tables. And the end-to-end latency is within a matter of seconds or even sub-seconds. Once we have the entity tables synchronized into our system, we can use Flink to do dimension table joins in a streaming fashion. The joined data gets further processed and will generate basic features, including things like the inventory of an item or the demographics of a user, etc. Such basic features are made available to our downstream recommendation systems. In addition to these basic features, our system also employs a large number of derived features, including the number of clicks for an item in the last 5 minutes, the number of page views for the last 7 days, etc. Depending on the time granularity, we may decide to do such aggregations in a streaming fashion using Flink. For example, we can make use of the window aggregation functionality in Flink to do this. If the time granularity is very large, we may also decide to do it in a batch fashion. In addition to this, our data scientists will want to understand our users' behavior and our products better, so he can figure out the best model for our search and recommendation services. In addition, our product operation teams may also want to gain insights about our products and the users so they can make the best promotion decisions. They will need to do a lot of interactive analysis of the data that we have in our system, and we use BI tools to do that. So as we can see, to build such an application, we will need a lot of different patterns in terms of the storage and the data access. To do efficient streaming joining, our dimension tables have to be very good at point lookup or serving queries. For this, we usually choose Cassandra, HBase, or Redis to store our dimension tables. And to do efficient analytics, our developers may decide to use Druid or Greencloud or ClickHouse for this. And for batch aggregation, people may decide to use Hive for that. So to build such a pipeline is becoming pretty complex. Where does such complexity come from? And to answer this question, I want to start with the Lambda architecture. Lambda architecture starts with a batch layer, which will process all your data at once periodically. For example, once every day. It will generate the full result. Obvious drawback is that the data is not always fresh. So Lambda architecture proposed a speed layer, which will process new incoming data, potentially in a streaming fashion. The output will be stored in a real-time data store. Our downstream applications will combine the output from the batch layer and the streaming layer to gain the latest view of the system. Obvious problem in this approach is the complexity. Because our user will need to write a job for the batch layer as well as a job for the streaming layer. Maintaining two jobs and make sure they are consistent with each other can be pretty hard if the application is having some complexity. This is where Flink comes into place. Flink adopts a unified approach to batch and streaming. You can write a single Flink job, and it can run in both batch mode and streaming mode, and they are guaranteed to be consistent with each other. So this solves the problem with data processing. What about the storage? The output of batch jobs are usually stored as a set of files in a distributed file system, such as HDFS. On the other hand, the storage for streaming jobs are much more complex story. There are a lot of choices for real-time storage. Let's take a look on all the different choices out there. In this slide, I listed some popular choices for storage in the open source world. We have HBase and Cassandra, which use raw storage, and they are good at doing point lookup queries or serving queries. We also have ClickHouse or Druid, which use current storage, and they are good at doing analytic queries. The proliferation of so many different storage systems is actually a manifestation that none of the storage system is good enough to meet all the needs of our applications. So our application developers have to choose among these different storage systems. Even worse, if the application is of any reasonable complexity, our application developers will usually be forced to choose more than multiple such systems. When this happens, the data will be stored in multiple systems. This will create data silos. It will increase your hardware cost because data may need to be duplicated unnecessarily in multiple systems. You will need to synchronize data across different systems. This can be extremely challenging in the case of real-time data. Making sure the data are consistent between these different systems is a non-trivial task. It will increase both the complexity of architecture and the complexity of operations. Learning a new product is hard. Each product comes with its own pitfalls. It only gets worse when our application developers need to learn multiple such products. So in an ideal world, we would like to have a single unified storage system that can store the outputs for both the batch jobs as well as the outputs of streaming jobs. Our downstream applications can access the data stored in this storage system in all different kinds of access patterns. This kind of new architecture is called hybrid serving analytic processing, or HSAP in short. An HSAP system provides a unified data storage for output generated by both batch jobs and streaming jobs. Once the data is inside the HSAP system, it should be able to provide all kinds of different data access to our downstream applications. On the bottom of this slide, I did a simple classification of various data access patterns. On the rightmost, we have the transactional data access pattern. This is probably has the most stringent requirement in terms of both SLA and latency. Then we have the serving workloads. A typical serving query is a point lookup. These queries are usually pretty straightforward, pretty simple, but in terms of latency requirement, it's pretty stringent, usually in a matter of milliseconds, and there is usually a very high concurrency requirement for serving queries. Then in the middle, we have the interactive queries. Usually, some human being will be submitting such queries and waiting for the result. So even though the query can be much more complex than serving queries, but we still expect such interactive queries to return in a matter of seconds or even sub-seconds. Now, on the leftmost, we have batch jobs. They will process a vast amount of data, but these jobs are usually scheduled periodically and no human is waiting for it. So there is no strict requirement or expectation in terms of latency. An HSAP system should be able to meet the data access patterns ranging from serving to interactive analytics all the way to batch processes. HSAP is not the only attempt that tries to address the complexity problem in a Lambda architecture. The data lake guys also try to solve the same problem. The tables in data lakes can be classified into two categories. There are these raw ingestion tables, which contains the raw events, and the tables for storing the curated data. For example, the refined tables, the feature tables, the aggregation data tables, etc. The idea is that instead of doing a periodic batch job, which reprocesses all the data in your system, we can do such process incrementally. For example, we can schedule an incremental ETL job that runs every 10 minutes or every hour that just process the new data that is available in the raw ingestion table and update the curated data, the curated tables. With this approach, it was able to improve the freshness of the data greatly without the complexity of Lambda architecture. There are two major differences between HSAP and the approach by data lakes. The first difference is that the data lakes approach still use a periodical ETL job. So there is still a latency of 5 minutes, 10 minutes, or even up to an hour. On the other hand, a HSAP system will process incoming data in a streaming fashion and populate it in the storage immediately, and this data will immediately available for querying. So it can achieve end-to-end latency in a matter of seconds or even sub-seconds. The second big difference is that the storage presented in data lakes are usually only good for analytic workload. But as we have seen in a true streaming system, serving queries are as important as analytic queries. We will need these serving queries to do streaming joins among a lot of other things. So in other words, the data lake approach is a macro batch solution to the complexity problem of a Lambda architecture. On the other hand, HSAP is a true end-to-end streaming solution to the same problem. Here, I make some quick comparison between HSAP versus HTAP and the OLAP system. From time to time, there may be a need to analyze data stored in a transactional database. The traditional way of doing that is to synchronize this data into an OLAP system and do the analysis in the OLAP system. The idea of HTAP is that why don't we analyze the transactional data directly in the database? On the other hand, an HSAP system will need to analyze both transactional and non-transactional data. The non-transaction data will include all types of events generated by interactions when our user interact with the platform. User will usually make a lot of clicks, maybe hundreds of clicks before he make a single purchase. So you can imagine the number of non-transactional data is actually orders of magnitude larger than the amount of transactional data. So as a result, an HSAP system need to be able to handle extremely high throughput real-time data ingestion. And the ingested data should be made available for querying instantly. On the HSAP system also supports the hybrid workload. It supports both serving and analytic workload. A serving workload usually have a very high concurrency requirement. We have seen systems that is submitting hundreds of millions of serving queries per second. So HSAP system needs to be really good at high concurrency. At the same time, because we support a hybrid workload, the serving queries have a latency expectation in a matter of milliseconds, while interactive analytic queries usually have a latency expectation in a matter of seconds or a bit longer. So workload isolation is also critical in HSAP system. We want to make sure the large complex analytic queries do not have adverse impact on the quick small serving queries. On the other hand, a pure OLAP system is usually have a much lower throughput requirement in a matter of dozens or maybe hundreds, maybe 1,000, and the workload isolation requirement is much weaker. To implement such a system, we build Holographs at Alibaba. The name Holographs coming from holographic Postgres. As you can imagine from this name, Holographs is compatible with Postgres. The word holographic actually comes from black hole physics. Imagine you are throwing a book into a black hole. Once the book crosses the horizon or the boundary of the black hole, it can never come back. You can never take it out. You might think the information that is contained in the book is lost forever because you can never get the book out and look at it. But that cannot be true because it would have violated one of the fundamental principles in quantum physics. Information cannot be created or destroyed. A potential way out of it is the holographic principle, which states that the horizon or the boundary of the black hole actually acts as a hologram to what is happening, what is contained inside the black hole. So to retrieve the information about what's contained in the book, you actually do not need to go inside the black hole to get the book out. You can directly look at what's on the boundary or on the horizon of the black hole and retrieve all such information. Similarly, with holographs, we will be able to ingest all your data, store all your data, and if you ever need to retrieve information or gain insights about your data, you can use the query engine provided by holographs to get that information easily without ever need to move the data out of the system. Holographs has been battle tested in Double 11 shopping festival at Alibaba. Last year, we were able to ingest 130 million events a second at the peak. All ingested events are immediately available for querying. At the same time, we served 145 million queries per second. This includes high concurrency serving queries, as well as the complex analytic queries. Our product team saw improved efficiency because of this simplified architecture. And you do not really need to learn a new product because Holographs is compatible with Postgres. So all your knowledge about the database, especially in Postgres, will be immediately transferable to Holographs. You can make use of the JDBC, ODBC drivers provided by Postgres to connect to Holographs. You can use the administration tools provided by Postgres to manage Holographs. And you can even use the documentation for Postgres. If you ever wonder how to write some query, you can do a search on Google. The chances are you will find the solution, and the solution will be applicable to Holographs as well. You can even use your favorite BI tools, such as Tableau, to connect to Holographs and analyze data that's stored there. Holographs adopts a compute storage disaggregation architecture. We build a high-performance C++ native engine. Before I go into more architecture details, I would like to show you some performance numbers first. An HSAP system supports both a serving and analytic workload. For serving workload, we compared against the HBase using YCSB benchmark, and we saw a 57x improvement in terms of performance. On the other hand, for analytical workload, we compared against the Greenprom using the TPCH benchmark. Again, we see order of magnitude in terms of performance. As I just mentioned, workload isolation is a critical requirement for HSAP system. We want to make sure the big complex analytic queries do not have adverse impact on the serving queries, which are performance and which are latency sensitive. So in this experiment, we have a foreground connection which continuously submit serving queries or point lookup queries. And we keep adding more and more background analytic queries to our system and observe how the latency of the serving queries change. As we see in this diagram, the latency of our serving queries hardly changed when we add more and more analytic workload. So Holographs was able to provide a good isolation between these different workloads. Now let's get a bit more into our architecture. There has been a long debate between shared storage versus shared nothing architecture in distributed database systems. In a shared storage architecture, all the data is stored in some common storage layer, and all data is accessible and manageable by any node that is present in your cluster. So there got to be some coherency protocol between these different nodes to make sure that data are consistent among these nodes. As a result, a shared storage system can hardly scale beyond a couple dozen nodes. But there is an upside to this approach. Imagine what happens when you add a new node to the system. Because the data is available in a common storage layer, this new node can immediately start serving new queries. So adding new machine to such a system is very easy. To quickly summarize, a shared storage system is not good at scalability, but it's very good at elasticity. On the other hand, a shared nothing architecture will partition your data, and each node will only be managing part of your data. Because at any time, a piece of data is only managed by a single node, there is no need to do coherency protocol between among these nodes. As a result, a shared nothing architecture can easily scale beyond hundreds of nodes. On the other hand, if we add a new node into a shared nothing cluster, this new node would have no data to start with, so it can hardly serve any traffic. We have to move data into this new node before it can do anything meaningful. So to summarize, a shared nothing architecture is very good at scalability, but it's not good at elasticity. There seems to be this trade-off between scalability and elasticity, but that does not have to be the case. There has been so much advancement in network technology in the last decade. The bandwidth has improved several orders of magnitude to the extent that it's no longer an issue for a lot of systems. So a new architecture emerged, and this is the compute storage disaggregation architecture that Holographs uses. In this architecture, Holographs will store all the data in a distributed file system, such as the HDFS or Pangu on AliCloud. All the computations are done in worker nodes, and these worker nodes are scheduled by Kubernetes. With this new architecture, Holographs was able to achieve both scalability and elasticity at the same time. Let's take a look how we did it. The tables are partitioned into many shards horizontally. Several tables may be partitioned in exactly the same way, and when this happens, we will group these tables together as a table group. So as a consequence, a table group gets partitioned horizontally into table group shards. In this picture, we have table A, table B, table C, and table D. They form a table group, and this table group is partitioned into 6 table group shards. These 6 table group shards gets assigned to 2 workers in our system. And so each worker gets assigned 3 table group shards. Because at any given time, a table group shard is only managed by a single node. So there is no necessity for coherency protocol between these 2 nodes. As a result, our system is able to scale as well as the shared nothing architecture in database world. Imagine what happens when we need to add new capacity into our system. If we need more storage space or more IOPS, we can simply add new machines to our distributed file system, and they will take care of it. In the case that we need more computation power, let's add a new worker node into our system. We can quickly move some table group shard to this new worker. Note that this movement of table group shard is actually a movement of computation, not a movement of data, because all data are stored in the distributed file system, such as HDFS. So this can be achieved very quickly in a matter of seconds. As a result, our system will be able to add new computing resource just as quickly as in shared storage system. So Holographs is able to achieve both scalability and elasticity at the same time with this new architecture. After we solve the scalability and the elasticity problem, we want to make sure our system is always performant. And we will start with the storage layer. We want to make sure our storage layer is flexible and performant. Table group shard is the basic unit in our storage layer. Because we provide real-time storage, we also employ write-ahead logging mechanism for any insert, update, delete to our system. Whenever we do that, we first will log a record, and a WAR manager is responsible for persisting this log record. The actual data will be stored in LSM structured tablets. The tablets come in 2 forms. We have columnar tablets, which are good at doing analytic queries, and we also have row tablets, which can efficiently do point lookup queries. We offer both types of tablets, so our application developers can choose between these formats according to the needs of his applications. But they don't have to be exclusive. A table can have both. A table is allowed to have multiple indices. For example, table A stores the data in columnar format, which is good for analytic workload, but at the same time, it also created a row index. So this table A will be efficient for both analytic workload and serving queries. This flexibility allows our users, allows our application developers to achieve the optimal performance in all types of different workloads. On the query side, we also want to make sure our performance is as good as possible. The key idea is to make sure we can use all the hardware resources. For this, we want our query engine to allow a massive level of parallelism. When a query enters into our system, it gets compiled and generated a query plan. A query plan will contain multiple operators. This is a very simple example of a query plan. The operators in our query plan can be classified into two types of nodes. We have the leaf level operators or leaf level fragments, which may lead to which will read the data from our storage system directly. Then we have the non-leaf level operators. These operators will do pure computation and do not directly read from our storage system. Scaling out the non-leaf level operators are straightforward. These operators can be allocated, scheduled onto any worker nodes because they do not need to read data directly. We can create as many operator instances for these operators as we want, as the cluster's resource allows. On the other hand, the leaf level operators have to be scheduled on the work node, which manages the table group shard. Fortunately, the scan operator and the write operators in our query engine are very scalable themselves. For example, a scan operator is not monolithic. Instead, it's broken down into a lot of work units. For example, we will create a work unit for each file contained in a tablet. A tablet can contain thousands of files, so this will give us thousands of work units, which can be parallelized. As a result, our query engine is able to achieve high parallelism for both leaf level and non-leaf level operators. So even if there is only a single query that's running our system, we will be able to make use all the hardware resources and achieve the optimal performance in our query processing. To achieve such a high level of parallelism, using operating system thread can introduce considerable overhead. In a lot of cases, we have done some experiment and observed that if the number of system thread is very large, the system scheduler can take over 50% CPU in just doing scheduling alone, and we want to avoid this overhead. So we introduced the concept of execution context. Execution context is basically a user space thread. An execution context is responsible for scheduling the work units we just talked about. The execution contexts themselves are scheduled by operating system threads. A single operating system thread can schedule a lot of execution contexts. As a result, the number of execution contexts are much larger than the number of operating system threads. So typically, we will create a single operating system thread for each core that we are allocated. This will greatly reduce the overhead from operating system scheduler. When we have multiple operating system threads in our system, there can be some load imbalance among these operating system threads. So we also have a scheduler that tries to load balance the execution context among these operating system threads to achieve the best utilization of hardware resource. Another thing I want to note is that our scheduling is cooperative, meaning this piece of code can never be preempted unless it explicitly yields or waits. This is nice because in a lot of critical paths, we can completely skip locking when we modify some key data structure because we know this piece of data can never be preempted. This further improves the efficiency of our system. As a result, we were able to achieve extreme high level of parallelism with very little overhead using this approach. To provide good isolation between among different workloads, we introduced that concept of a scheduling group. A scheduling group basically is a unit of SLA. For example, we create a scheduling group for each analytic queries. So our scheduler understands the SLA requirement for each query. So they can make the best scheduling decisions to guarantee the SLA for both serving and analytic workloads. Now let's go back and take a look at our real-time recommendation systems. All the events that's generated through the interactions from between our user and the platform gets collected in this queuing system. And this Flink will read from the queuing system and process all these events. Flink is used to do both feature engineering, just as we explained in the beginning of this talk. And it's also used to do machine learning on top of such data, to do model training on top of such data. The data are stored in Holographs. It includes the event tables, the dimension tables, as well as the outputs from Flink jobs. Our downstream applications will access the data stored in Holographs in all kinds of different data access patterns. For example, through point lookups or interactive analytics, etc. As we can see, with HSAP, the architecture gets greatly simplified. Our users no longer need to deal with a lot of different products. To summarize, with Flink and Holographs, we were able to implement a hybrid serving and analytical processing architecture. This simplified architecture allows us to do true end-to-end streaming. And this will make your data more real-time. And when this happens, you actually get more value out of your data. So it can really boost your business and reduce your total cost of ownership. To find out more information, please visit us at holographs.io. You are also welcome to follow us on Twitter. Thank you.